All right, let's dive into one of the most legendary sorting algorithms out there, Quicksort. It's a powerhouse, a staple in computer science, but it's got a few secrets up its sleeve that we are absolutely going to unlock today.
So what if I told you there's an algorithm that is blazing fast? I mean, the kind of speed that powers huge real-world systems, but it has a hidden dark side. One wrong move, and it can slow to an absolute crawl. That's the whole paradox of Quicksort. Its average speed is incredible, but its worst-case performance? A total disaster waiting to happen.
But you know what? That fragility is exactly what makes it so fascinating. Because if we can understand how it works and how it breaks, we can control its power. And that's our mission today. We're going to master the strategies that make Quicksort not just fast, but totally reliable and robust.
So how does this thing actually work? Well, at its core, Quicksort is the perfect poster child for a super powerful strategy called divide and conquer. The name says it all, right? It's all about taking a giant, messy problem and just breaking it down into smaller, much easier pieces.
Okay, here's the textbook definition. Quicksort grabs one element, we call this the pivot, and then it just rearranges everything else. Anything smaller than the pivot gets shoved to one side, and anything bigger gets pushed to the other. After that, it just does the exact same thing to those two new smaller groups. That's it. Let's make this way more tangible. Imagine you've laid out a scrambled line of numbered cards on a table. First step, just pick any card. That's your pivot. Now, step 2, you go through all the other cards. If a card is smaller than your pivot, you slide it over to the left. If it's bigger, you slide it to the right. And finally, you just do that all over again for the pile on the left and the pile on the right. And you keep going until you're just left with single cards. Pretty simple, huh?
And that brings us to the absolute heart of the matter, the single most critical decision in this entire algorithm, how you choose that pivot. Seriously, this one choice is the difference between lightning fast and, well, a complete catastrophe.
So, how do you pick a good pivot? Well, the easy, kinda naive way is to just grab the first or last element every time. Simple, sure, but it's brittle. If your data happens to be already sorted, this choice sends you straight into that worst-case disaster. The smarter play is something called median of 3. You just look at the first, middle, and last elements, and pick the one that's in the middle. It's a tiny change, but it makes the algorithm way, way more resilient.
And this chart, this shows you everything. A good pivot gets you what we call O(n log n) time, which is incredibly fast and efficient. But a bad pivot, you crash down to O(n squared, which for a big list of numbers is just painfully, brutally slow. I mean, we're talking night and day difference here.
So the key takeaway on pivots is this. You've got options. A fixed pivot is simple but risky. Picking a random pivot is actually a fantastic way to pretty much guarantee good performance on average. But for most situations, median of 3 is your go-to. It's that perfect sweet spot between being simple and being really robust.
Okay, so we've picked our pivot. Now the real work begins. We have to actually do the rearranging, right? This process is called partitioning, and you can think of it as the true engine room of the whole Quicksort algorithm. This is where the magic happens.
And it turns out there's more than one way to partition an array. You've got a few key schemes. The Lamuto scheme is super simple to understand, which makes it great for learning. Then you've got the horse scheme, which uses 2 pointers that scan inwards. It's usually faster in the real world. And then there's this really cool specialist, the 3-way partition, which shines when you have a ton of duplicate numbers.
And this is where that 3-way partition becomes a total game changer. Think about it. If you have tons of numbers that are the same as the pivot, a normal partition just wastes a bunch of time swapping them around. A 3-way partition is smarter. It groups things into 3 piles, less than, equal to, and greater than the pivot, all in one go. For those kinds of data sets, it can take you from great performance to something that's almost perfectly linear. That's a huge speed up.
Okay, so we've been deep in the weeds of pivots and partitioning. Let's pull back for a second. How does Quicksort actually stack up against the other big-name sorting algorithms? Knowing its trade-offs is everything when you're deciding what tool to use.
In this little showdown, you can see the trade-offs crystal clear. Merge sort, for example, guarantees that fast O(n log n) time, but it's a memory hog. Heap sort is also guaranteed to be fast and uses almost no extra space. Quicksort's claim to fame is its incredible average speed and the fact that it sorts in place, meaning it does all its work right inside the original array without needing a bunch of extra memory. All right, Let's distill all of this down into what really matters, especially if you're gearing up for a coding interview. Think of this as your Quicksort cheat sheet for when you're under pressure.
Here are the non-negotiables. First, pivot choice is everything. Talk about median of 3 or randomized. Second, know the difference between Hoare and Lamuto partitioning. Third, remember that three-way partition is your secret weapon for duplicates. Fourth, here's a pro tip. Always recurse on the smaller half first. It's a clever trick to minimize memory usage. And finally, never forget, Quicksort is fast, it's in place, but it is not a stable sort. That means if you have two identical items, their original order might get swapped.
And honestly, this quote just nails it. Yeah, there's that scary worst-case scenario, but Quicksort's incredible average speed and its memory efficiency, the fact that it's so cache-friendly, is why it's been a cornerstone of high-performance computing for decades.
So there you have it. Once you master how to pick a smart pivot, use the right partition scheme, and handle the recursion correctly, you've basically tamed the beast. Quicksort goes from being a fragile, risky algorithm to one of the most powerful tools in your entire toolkit.
You've mastered sorting an entire array. Awesome. But let me leave you with one last thought. What if you don't need to sort the whole thing? What if all you need is, say, the 5th largest number, or the 100th smallest? Well, it turns out that partitioning logic we just learned is the secret to solving that problem even faster than a full sort. But that's a story for another time.